Okay, so section 5, we're going to yet again learn something um, of how to do systems of equations, how to solve them in yet another way. So you've already done solving it by hand. You've done the 2 by 2s in substitution and elimination. You also did those great big problems by elimination where you had the X, Y, Z, and that was a lot of fun. And you also had the calculator at your disposal. And we have matrices. And the whole purpose of using matrices is so that you can solve systems of equations to find the point where those lines intersect. And then we have reasons for why we have to do that, and we'll go into that into class. Um, but we have all this vocabulary. Determinants, second order determinant, which is a determinant of a 2 by 2 matrix. And a determinant is a tool for doing other things. So we'll get into that. And then a third order determinant is a determinant of a 3 by 3 matrix. Then we've got the diagonal rule, which is how we find a determinant. And then using those determinants in Cramer's rule. And then we use a coefficient matrix in Cramer's rule. So moving forward. So here's Cramer's rule. Every square matrix has a determinant, and of course a 2 by 2 matrix is called a second order determinant. So to find a determinant of this 2 by 2, which has 4 elements in it, A, B, C, D, notice you've got different brackets of a matrix and a determinant. So if you are finding a determinant, it says, hey, do a determinant. It doesn't just mean, hey, you've got a matrix. It means do something, do this. And it means for you to take A, multiply it down, do that cross multiplication, and multiply A times D, and then subtract C times B. So you've got that cross multiplication. So here's your example. If you had a 2 by 2 that has 4, 5, negative 3, 6 in it, then you would do 4 times 6 minus 5 times negative 3. That's going to result in 39. So then you've got these two other examples. And so the resulting determinant there is 22, and the resulting determinant for this other little determinant is negative 73, and you can check that later. You can also use determinants to find the area of a triangle. So there's this cool little formula here, and this is absolute value. So note that those aren't just little brackets. Those are absolute value of the area, because you might come out with a negative number. Of course, area is not negative. You actually have positive area because you're finding, space. You're finding actual square footage or square units of something. It would come out negative if, for instance, you had points over in your second and third and down here in your fourth quadrant. So what you do is you have these points, which become two of your columns of your determinant matrix, and then you put ones in here. Ones because if you multiply by 1, it does not change the value of your numbers. And then, of course, half. Where does half come in? Think about your area formula of a triangle. Why would you have a half? Maybe because of that normal formula. And so you write your determinant, and then we do the diagonal rule for a 3 by 3, and I can show you what that actually looks like. But we're going to do the calculator for a 3 by 3, and there should be a time symbol right here, which has gone missing. But I'll show you what that very large, very fun diagonal looks like for a 3 by 3. Much more involved than the 2 by 2, which is kind of friendly. Here's Cramer's rule for a 2 by 2 system. If C is a coefficient matrix for a system of equations, then you've got this 2 by 2 matrix, so coefficients, and then you have the solution to your system, which looks like this. So maybe that'll be a little more fun language here in a second. So let's solve this using Cramer's rule. So where did all this come from? So to solve x, we pull m and n. What are those? Well, those are those constants at the end of your system, meaning the answers that you guys like to say all the time. Where do these b and g numbers come from? Well, those come from your y values. So we're filling out our x value determinants. Now remember, c is supposed to be your coefficients, just the coefficients from here in your system. So your x values, your y values, those coefficients. And then also you need to do y. So this is how Cramer's rule is set up. Y is going to be equal to these two determinants divided into each other. A and F come from the x values. So we have x over here. And then we're going to replace this column is going to be those constants. So we set those up, and notice the brackets. You're supposed to be finding determinant, 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 and then you have the division, so you divide, and you get these nice, neat answers. Reminder, there at the bottom, you're dividing by the same thing, same determinant here at the bottom, so that gets used again and again and again. That's why it just says C here, means determinant of your coefficients. So on the next page, this just shows you all the math that's involved. So this is just the math of those determinants. Remember the simple cross multiplication from the very beginning of your notes? So what it comes out to is really you're cross multiplying and subtracting. Okay, this is going to be the same coefficient matrix determinant, so you'll have the same number, notice. So you really won't need to do that more than once, and it comes out to a very simple answer. This should, once you get used to setting up Cramer's rule, seem much faster, much easier than the substitution method from chapter 3, the elimination method from chapter 3. So once you get it and once you understand the setup and it clicks, you'll go, oh yeah, that was way faster than what we had done before. And of course you have an x value, you have a y value. It means you have found a point. So we have another tool for finding the solutions to a system of equations, which is ultimately two lines intersecting somewhere in the coordinate system. So with that point where they intersect, or maybe they don't, maybe we have an infinite set of solutions, or maybe there's no solution because they're parallel lines. And that is what we're looking for.